Hello and welcome everyone to our second video, our second in-class video that is about 11.10. And again, a little bit of a disclaimer here, depending on if you're looking in the book or if you're looking at web work, these sorts of problems may either appear in section 10 or section 11. So if you don't see any of these, for instance, in web work and under section 10, right, they're actually in the section 10/section 11 category. So anyway, in this video, we're going to be talking about what can Taylor and Maclaurin series actually be used for, right? Last time, in our last class video, we did some work on actually calculating these things out. But the question has to be asked, well, why are we calculating these things out? What are they good for? And so I'd like to give you maybe three nice uses for Taylor and Maclaurin series or polynomials. And so the first is, right, for a long time we've only been able to say what geometric series converge to, and in some special cases like telescoping series and things like this. But with using Taylor and Maclaurin series and polynomials, we'll be able to say what a good number of non-geometric series actually converge to. So that's the first thing. Next, there's going to be some cases where we can calculate limits faster. Instead of using L'Hopital's rule over and over and over again, we can actually use Taylor and Maclaurin series to calculate out some limits. And then the third thing is that we're going to evaluate integrals of functions that don't have elementary antiderivatives. And so that's kind of at the beginning of chapter 11, I told you guys that this is one of the main uses, right, that Newton, when he would calculate out integrals, he would turn things into infinite polynomials, and then those are really easy to integrate, right? Polynomials are easy to integrate, and so he didn't have to deal with things like integration by parts or partial fractions or things like this, right? He would just turn things into infinite polynomials, aka power series. So that's what we're going to be doing here. Okay, so let's get to it with this wonderful historical problem I'd like to start us off with. Euler, one of arguably like the best mathematician of all times, in 1748, right? He's the one, Euler's constant, this 2.718, in fact, it's right here. So he gives the decimal expansion. And remember, kind of, this is all based off of the natural logarithm, right? The natural logarithm was discovered first, right? What is this quadrature of the hyperbola, or the area under 1 over x sort of deal? And then you have to ask, well, it's 1-to-1. It has an inverse. What is its inverse? And so he says, right, that this is this value e. And if you want to calculate out e at home, right, so he gives the decimal expansion and, quite a few digits there. But he says, if you want to calculate out e at home, here's how you do it with this infinite series. So 1 plus 1 plus a half, right, and so on and so forth. And you have to say, well, where does this come from? Why is this true? And actually, we can prove this using the power series for e to the x. So that's what I'd like to do in this first example right here. So this is true using the power series for e to the x. So I would like to remind us that e to x is equal to, and that's n from 0 to infinity, right? Summing these things up, x to the n divided by n factorial. Or if we were to write this in its expanded view, right? First off, we would plug in 0 everywhere we see an n, so x to the 0 divided by 0 factorial. Then we'd plug in a 1 everywhere we see an n. Then we'd plug in a 2, so on and so forth. I'll do just a couple more here. There we go. And so if we wanted to calculate out e itself, right, e to the first power, right, let's plug in a 1 everywhere we see an x. So if we plug in a 1 everywhere we see an x, we would get, summing up from n equals 0 to infinity, of 1 raised to the nth power divided by n factorial. Well, 1 raised to any power is just 1. So we could do this. And notice that this right here is not a geometric series, right? It's not a times r to the n. And yet we can say that when you sum this all up, it's equal to e to the first power. And this is, of course, relying heavily on the fact that the radius of convergence for this power series is infinity. Otherwise, you couldn't just plug in any old number willy-nilly. But notice what happens here. If I plug in 1 everywhere I see an x, well, 1 to the 0 power is going to be 1. Divided by 0 factorial, that's 1. 1 to the first power, 1 divided by 1 factorial, that's 1. 1 squared, that's 1 divided by 2 factorial, that's 1 times 2. 1 cubed, that's 1 divided by 3 factorial, 1 times 2 times 3. 1 to the 4th power is 1. 4 factorial is 1 times 2 times 3 times 4. And this keeps on going. I should have that up there as well. And notice that this is exactly what Euler claims right here. Is our answer there. So yes, indeed, that this would sum up and give you E. And so you can kind of take this as far as you want to go and kind of do your own approximation for E. So if you want to stop after 20 terms or 30 terms or whatever, right, however bored you are, right, you can just keep on taking this and that will give you a better and better approximation for E. Okay, let's play this game again with something a little bit more complicated, right? So we have something like this. And what I would recommend is that we go back to that list that we have from our first video in 11.10, and we try to eyeball this and see kind of what it looks like, right? And so I noticed that, for instance, we have natural log of 2's being raised to higher and higher powers, and it looks like we're dividing by factorials. So we have maybe 1 factorial here, and, well, I guess we could write this as 0 factorial, maybe if we want to follow a pattern. And we may also notice that 1 is the same thing as the natural log of 2 raised to the 0th power, even. So it seems like we have bigger and bigger powers of the natural log of 2. We have this factorial and everything. And so let me go ahead and rewrite this maybe in sigma notation, what I think this is in sigma notation. So it's like summing up from maybe n equals 0 to infinity. It looks like we have the natural log of 2 raised to some power of n. So again, first we have 0 powers, 1, 2, 3, so on and so forth. And then we're dividing by factorials, right? And so divided by n factorial. But I also see that there's this alternating piece. And so the alternating piece, that's probably the same thing as like -1 to the n. And so again, what I would do is I'd go back to this table that we had back here, that we have on our formula sheet, for instance, and I would try to say, okay, which one of these looks like what I have? And so notice we had just n factorial, so I like the fact that E has this n factorial on bottom. This one just has odds, right? 2n plus 1 factorial, so I don't like that one nearly as much. This one just has even, so I don't like that nearly as much. This one just has n, so no n factorial or anything like this. And this one doesn't divide by anything. And so right now, I'm thinking, okay, maybe I can use E here. So, okay, let's try this again. Notice that we have x to the n divided by some n factorial. So let me go back to my problem here. There it is. And so I need to try to see what this is. N equals 0 to infinity, and I have x to the n divided by n factorial. So again, this is supposed to be e to the x here. And so notice that I have a couple things that are both raised to the nth power. So let's maybe combine these here and say that x should be the negative natural log of 2, all raised to the nth power. And so that is, I'm substituting everywhere I see an x, I'm going to put the negative natural log of 2. The negative natural log of 2. And so we could simplify this, right? We could take that negative sign and turn it into the exponent. This is just using the power rule for logarithms. And now we have that e and that natural log will cancel with each other. And so we're just going to be left with 2 to the negative first power, or that's the same thing as 1/2. So that is, when you add up all of these values right here, going on forever, you're going to get closer and closer to 1/2. So again, this is not a geometric series, and yet we can say conclusively, right, what it converges to. So not just that it converges, but what it actually converges to. So that's something that, again, previously we had not been able to do that except for with geometric series. So this is something, some improvement that we've been able to make thanks to the power of Maclaurin and Taylor series. Okay, so here I have another problem that's in the same sort of flavor, a very famous historical problem here, and I'd like to show you that using arctangent, that is tangent inverse of x, we can actually say what this here converges to. So remember, tangent inverse wasn't actually on our list up above, so we need to come up with this again. So if you happen to remember it, and this is given in the book, you could just go ahead and write down, and I'll tell you that tangent inverse of x is equal to summing up from n equals 0 to infinity, and it's alternating. It only has odd powers, so x to the 2n plus 1 divided by 2n plus 1. So we're going to try to make this look very similar to what we have up here. And so you can already kind of see a lot of the pieces coming together. But let's suppose that you didn't happen to have this memorized, which is completely reasonable as well. So what we would do is remember kind of when we were bringing these things up back in 11.9, we would say, well, let's take a look at the derivative of tangent inverse. So here's tangent inverse. When we take its derivative, we get 1 over 1 plus x squared. And this is something that we can actually find a power series to, thanks to the stuff that we learned in 11.9. Right? We try to make it look like 1 over 1 minus u. And so let's go ahead and take u to be equal to negative x squared. And so if we take u to be equal to negative x squared, we'll so remember that the infinite polynomial for this is just summing up powers of u, so u to the n. And again, remember, u is going to be equal to negative x squared. So instead of u, let me go ahead and write negative x squared to the nth power. Or if we wanted to, we could go ahead and split this up. And again, this is going from n equals 0 to infinity. N equals 0 to infinity. And so let's see, we have a bunch of things raised to the nth power. So for instance, that negative sign is being raised to the nth power, or that's the same thing as negative 1 raised to the nth power. And then we have x squared raised to the nth power. And so when you have powers raised to more powers, right, they multiply together. So you get x to the 2n. And so the last bit is now if we were to integrate, and again, we're trying to figure out what is this infinite polynomial, or the power series for tangent inverse of x. Well, I would just need to integrate. And so notice that when we integrate, this constant is along for the ride, so it doesn't change. However, when you integrate x, or in this case x to the 2n, you need to raise up your power by 1, and then you need to divide by that new exponent. So that's exactly where this comes from. Again, if you happen to have it memorized, it'll save you 2 minutes, something like this. But if you don't, you can just recreate it rather fast. Okay. So let's go ahead and maybe write out the expanded form of this just to really see what it looks like. So if I was to plug in n equals 0, again, everywhere I see an n, I'm going to plug in 0. So let's see, negative 1 to the 0th power, that's just going to be 1. I'm going to have x to the 0 plus 1, that's going to be x to the first power. And I'm dividing by 0 plus 1, that's 1. Next up, if I was to plug in 1 everywhere I see an n, well, let's see, that'd be a negative sign because of this negative 1 to the nth power. I'd have x cubed, plugging in 1 for n, and I'd be dividing by 3. Next up, you can double check for me, but you'll get x to the 5th divided by 5, and this one's positive. Then minus x to the 7th divided by 7, and this one's negative, and so on and so forth. And so this is the infinite polynomial, or the power series for arctangent. And again, we would like to use this to say something about this infinite sum right here. So 1 minus a third plus a fifth minus a 7th plus a 9th. And you'll notice that this is looking exactly like what we have here, except for in the numerator, there's a bunch of 1s. And so I'm going to go ahead and replace everywhere I see an x, I'm going to put a 1. So tangent inverse of 1 is equal to 1 minus a third, right? Because 1 cubed is just 1, plus a fifth minus a 7th, so on and so forth. And we should remember, right, tangent inverse of 1 is equal to pi over 4. So pi over 4 here. And then the last thing, right, I told you that this is kind of a very historical problem, is that this is how you can calculate out pi. And so I'm going to go ahead and multiply by 4 on both sides, and we can get that pi is equal to 4 times 1 minus a third plus a fifth minus a 7th, so on and so forth, right? That this is going to be an approximation for pi. And you can get as good of approximation as you want by, again, just kind of adding and subtracting these reciprocals of odd numbers. So again, kind of a remarkable thing. Again, kind of a very famous type of problem here, and this is where it comes from. It's just really, it's the power series expansion for tangent inverse. All right, one more problem to go. I've been doing a lot of these and kind of not giving you a chance to work so much, so please, for this one, pause the video. I have two problems here. I just changed the parentheses slightly, right? And the answer changes quite significantly, actually. So please take a look at both of these. Again, go back to that list of Maclaurin series that we had at the beginning of our 11.10 notes. Take a look at those and see if you can get either one of these to match up with something that we had on that list. And then when you're ready, go ahead, unpause the video, and we'll spoil the surprise together. All right, so here are my answers that I've come up with. Actually, funny story. So the original problem that I had was this one right here. And actually, a few semesters back, a student misread it and thought that I had asked this problem right here. And I thought, oh, that's brilliant, actually. You know, this is a wonderful example on how just taking your time and reading the problem carefully can make actually a quite significant difference. And so let me go through kind of this one right here and what this one would mean. And so if you just have these parentheses on the outside of 2 and n factorial, I mean, it's kind of funny to even put parentheses there at all. But this just quite literally means 2 times n factorial. And so you can kind of factor out this 2, or 1/2, since it's in the denominator here. And then you can combine all of your things that have are being raised to the nth power. So there's the -1, there's the 4, there's the 9, right? And that's where this -4/9 to the nth power comes from. And then since we factored out that 2, you just have n factorial on bottom. And then when you go back and you compare it to the list of Maclaurin series, you notice that again, this is something that's very, very close to e. That this, remember, e is just x to the n divided by n factorial. So here, -4/9 is taking the place of x. So instead of x, we write -4/9, and this is what this power series actually converges to. So again, better than just saying it converges, we can say specifically now what it converges to. Okay, so that's kind of if you were to misread it. What I actually had intended for the problem to be is this one right here, where you have 2n all in parentheses, and then it's 2n factorial. So all of it has the factorial. And so, okay, when you go and you, again, kind of if you're thinking about trying to make it look like one of the items on the list, the only one that has 2n factorial in the denominator is cosine. And so you go and you try to manipulate this and you try to make it look a lot like cosine. Well, cosine has -1, right? So it's alternating. It has the 2n factorial. But notice in this step right here, if you were just kind of, again, trying to get to match up, you would have 4/9 raised to the nth power. But cosine needs something that's raised to the 2nth power, right? So you have to have 2n. And so you do a little bit of a trick here, right? And you say that, well, maybe I could write it down here as well, that 4/9, that's going to be the same thing as if I took the square root of 4/9 and I squared it. And so the square root of 4 is going to be 2, and the square root of 9 is going to be 3, and now we can square that. And when you take powers and you raise them to powers, right, in this case we're raising it to the nth power here, right, they multiply, and that's how you can create this raised to the 2nth power. And so this actually becomes 2/3 then, right, instead of 4/9. And now we have this set up exactly like cosine. So this actually is going to be a cosine of 2/3. So if you were to sum all of this together, the output would be it converges, and it converges to cosine of 2/3. All right, so that is the last problem kind of relating to finding what these series actually sum to, thanks to the Maclaurin series. Now let's go ahead and move on. And I said that in some cases, right, we can actually find limits a little bit faster than with L'Hopital's rule, thanks to these Maclaurin series and Taylor series. And so I'd like to give us just a little bit of a warm-up. You can argue that this wouldn't be any faster whatsoever to calculate out this limit using the Maclaurin series. I suppose, right, on a quiz or an exam, we could just say, hey, use this method, right? But let's go ahead and see how it's done. All right, so for this one, we're going to use the Maclaurin series, and notice that we know the Maclaurin series for sine. So we're going to use this fact here, that sine, and we'll say of u, is equal to, and again, we have all of the odd powers. So this is the first power, then the third power, then the fifth power. Remember that it's alternating, and that you divide by that odd factorial. So something like this. And it keeps on going. And right, our value here is that we have 3x inside of sine. So I'm going to go ahead and write, instead of u, I'm going to write sine of 3x. So we're going to have 3x minus 3x quantity cubed over 3 factorial plus 3x quantity to the fifth divided by 5 factorial, so on and so forth here. And then in order to create this whole division, right, sine of 3x divided by x, let's go ahead and divide through by x everywhere. And of course, when we do this, we can go ahead and simplify here. We're going to have 3. And let's see, we're going to have 3 cubed. And then one of the x's cancel, right? We're going to have x squared divided by 3 factorial. And then next up, we're going to have 3 to the fifth. One of the x's cancel, so we're going to have x to the fourth divided by 5 factorial. Then we're going to have 3 to the seventh divided by, 3 to the seventh times x to the sixth divided by 7 factorial, so on and so forth. And if we wanted to take the limit, right? So let's go ahead, I'll add a little bit more room here. The limit as x goes to 0 for this sine of 3x divided by x. The limit as x goes to 0 here, sine of 3x divided by x. We'll notice that this first term is the only one that doesn't have x's in it. All of the other ones have x's. And right, and as we keep on going, those powers of x's are going to get bigger and bigger and bigger. And so if all of the x's are going to 0, the only thing that's going to survive is this 3. We're going to have 3 minus 0 plus 0 minus 0 plus 0, right? But the 3 is the only thing that's going to actually, exist after we plug in 0 everywhere we see an x, right? And so the answer is 3. Of course, we can check this with L'Hopital's rule. This one's actually pretty fast, so you can check this with L'Hopital's rule, and that's completely fine. But this is how we can actually use Maclaurin series in order to calculate out some limits. Now again, this one wasn't really faster than using L'Hopital's rule. It's just kind of to illustrate the point. But here I have one where if you wanted to use L'Hopital's rule, you'd actually kind of technically have to use it 4 times. And so that's going to be quite a pain, right? And so I think that we can do this a lot faster if we use series, right? And so I'm going to go ahead. Notice that this one just says, right, to use series to evaluate this out. Of course, we have lots of polynomials here. The only thing that's not in a polynomial form right now is cosine. So let's go ahead and write this in its polynomial form, its infinite polynomial form. So the limit as x goes to 0, negative x squared over 2, that's fine. The 1's fine. And then minus now cosine. Now remember, the cosine, those are all the evens. It alternates. It starts with 0, right? So anything raised to the 0th power is just going to be 1. Minus x squared divided by 2 factorial, plus x to the 4th divided by 4 factorial, minus x to the 6th divided by 6 factorial, and you keep on going forever and ever, alternating just all of the evens. So again, this is what I would get directly from that list that we had at the beginning of 11.10 of different common Maclaurin series. We're going to take that, and then we're going to divide it by x to the 4th. So notice we can already see there's going to be some canceling that happens, right? We have a 1 minus a 1. We have a negative x squared over 2, and we're subtracting a negative x squared over 2, aka we're adding x squared over 2. 2 factorial, remember, is the same thing as 2. So we can go ahead, cancel a bit, and we're going to be left with the limit as x goes to 0. That's a horrible 0. There we go. And again, I still need to distribute this negative sign to each piece. So let's see here. We'd have negative x to the 4th divided by 4 factorial. we'd have positive x to the 6th divided by 6 factorial. Let's write one more. We'd have negative x to the 8th divided by 8 factorial. And again, this would keep on going on. We need to take that, and we need to divide it by x to the 4th. So let's see, there's going to be a lot of canceling that happens. For the first one here, we're going to have just negative 1 divided by 4 factorial. Here, again, we have 6 x's divided by 4 x's. Right, so this is going to be x squared divided by 6 factorial. Then after that, we're going to have minus x to the 4th divided by 8 factorial. Right, there's a lot of canceling that's going on. And we keep on going and going and going. And again, we're going to take the limit as x goes to 0. So as x goes to 0, again, all of these ones that have x's and kind of everything after it, because the powers of x's keep on getting bigger and bigger, they're all going to go to 0. And so the only thing that we're going to be left with is this negative 1 over 4 factorial, or that's the same thing as negative 1/24. So again, this is a way that we can use series to evaluate out limits. The last problem that I'd like to give you, this was a challenging problem on the exam, Spring Semester 19, Exam 2 challenging problem. Right, it just says to evaluate out this limit. It doesn't give any hints or anything like this. Of course, right, students probably realized, right, that L'Hopital's rule, that was primarily used in Chapter 6 and a little bit in Chapter 7 there. Right, but so maybe they were already thinking that there's a way to do this with using series, right? So, of course, maybe the quickest way or a very nice way is to use series for this. If you try to use L'Hopital's rule, some of these derivatives get quite messy, right? Look at this. The product rule in the bottom would be kind of a bit of a nightmare. And likewise, taking the derivative at the top, it doesn't look very fun either when you have to use the chain rule and all this sort of stuff. So please take a crack at this one. Pause the video. See how far you can get. Again, try to use series in order to evaluate this out. And then we'll come together and we'll talk about the solution. All right, so this is the solution that I came up with here. In the numerator, right, we have an e. So I'm going to go ahead and write out the infinite polynomial here for e. E to the u, and we're going to replace everywhere we see an u, we're going to put x to the 100th power. So the first one we have u to the first, so this is going to be x to the 100th power, then u squared over 2 factorial, then u cubed over 3 factorial, so on and so forth, and then we subtract 1 at the very end. Divide that by, we have x to the 10th, that's already a perfectly fine polynomial there. And then sine, remember that this alternates back and forth, and it has the odd powers of u, or the odd powers of x, if you will, divided by the odd factorials. So divided by 1 factorial, 3 factorial, 5 factorial, so on and so forth. And so if you take this and you raise it to the first power, you get exactly what you've put into sine, right? X to the 90th divided by 2. If you take it and you cube it, right, well, x to the 90th, and then you raise it to the cube power, right, you need to multiply by 3, so you get x to the 270th. Of course, 2 cubed is 8. That's where that comes from. And then you need to divide that by 3 factorial. And then you add on, you would do the 5th term, right, the x to the 5th stuff, and then x to the 7th, all that sort of stuff. Keep on going forever and ever and ever. And so let's go ahead and simplify and see what we get here. Right, so this one right here, we can go ahead and cancel out these 1s, 1 and negative 1. And then if we distribute this x to the 10th to each piece, here we can see that this is where this x to the 100th comes from. Now we have these like bases, so they add. And instead of x to the 270, I've written x to the 280. And I've just done some other small simplifying here and there. So now notice that both of these, the smallest power of x is x to the 100. So you can imagine factoring out an x to the 100 from the top and the bottom. Those would perfectly cancel, and then you'd be left with, well, just 1 over 1/2. And again, the rest of them, we're plugging in 0 as x is going to 0. And so all of the other terms would have x's remaining. And so right here would be 100 x's left over. Here there would be 200, so on and so forth, right? All of them have lots of powers of x. And likewise in the denominator, right? As x goes to 0, that's going to be taking care of a lot of the terms. And so we're going to be left with essentially 1 divided by 1/2. and that gives us the final answer of 2. So yeah, this is a rather clever problem, again, using series in order to evaluate out this limit, that otherwise, right, L'Hopital's rule would be quite a pain in order to evaluate this out. But yeah, it can be done relatively fast, but I think it certainly earns its name as a challenging problem, especially to show up on an exam. All right, so there's a couple of examples on how we can actually use these Maclaurin series in order to evaluate out limits a little bit faster. The last thing that I wanted to do in this video here is calculate out some antiderivatives, right, for things that really don't have elementary antiderivatives. And so I think it'd be fun, I'll show you really quick here, if you plug in this into Wolfram alpha, for instance. So here before class, I did plug this into Wolfram alpha. And so the integral of sine of x over x, and you get this, psi of x. And so actually, right, that's what I mean by having they don't have an elementary antiderivative. That is, there's no combinations of any square roots of any other functions that we know or love in order to represent this antiderivative here, that basically needs some new name. There is no way to kind of represent this using any of the functions that we know and love from any of our algebra or calculus before this. And so it needs, again, there's no choice. We have to call it something else. It's kind of like pi or e, right? They get these special symbols because there's no way to represent them using any combinations of roots or division or multiplication or any powers of things, right? They need kind of a new way to denote them. And so the same thing is happening here. So, and remember, sine of x over x, we've seen this several times, and we know how to take the derivative of this. Certainly we know how to take limits with sine of x over x, but the antiderivative of this is quite a horrible thing, you see. And so, right, you know, if Leibniz, you know, with all of his rules and everything, you know, integration by parts, you could spend, you know, an entire lifetime trying to solve this problem using any of our techniques from chapter 7, and there is no way, right? And yet, right, if you handed Newton this problem, he would say, well, I can use power series and I can at least approximate the answer. And so he's going to turn this into a power series and evaluate it. And so I'd like to show you how to do just that. So again, sine of x is something that we have a well-known power series for. So let me go ahead and write this down. Sine of x is equal to, and again, we sum up, and it's an alternating series, and it just has the odd bits. So, right, x to the 2n plus 1 divided by 2n plus 1 factorial in the denominator. All right, so if I wanted to take this and I wanted to divide by x, so divide by x on both sides, well then we'd get sine of x divided by x is equal to, summing up from n equals 0 to infinity, negative 1 to the n, and again kind of we have x to the 2n plus 1 on top. We're dividing by x, so that's going to cancel a little bit. It's going to cancel out one of them. So we're still going to have x to the 2n on top here. And we're dividing by this nice constant here, 2n plus 1 factorial. All right, so the last bit is, well, if I want to integrate it, well, we can just integrate term by term. So if I integrate term by term, right, the negative 1 to the n, this is constant with respect to x. The 2n plus 1 factorial is constant with respect to x. And so if I wanted to integrate x to the 2n, well, I would raise up my power by 1, so I'd go to 2n plus 1, and I would divide by my new exponent here, 2n plus 1. And this right here is what the power series, or the approximation for this psi of x, right, this si of x, this integral of sine of x divided by x. So using power series, we can actually evaluate this, and then of course we could plug things into it, right? If you wanted to know what the integral of this thing was, for instance, from 0 to 1, right? We could plug in zeros and ones and we could get a good approximation for this. So, okay, this is what we mean by using power series in order to evaluate out some of these integrals here. And so I have one more example. I'd like to give you a chance to try one. This is another one where kind of try as you might. There is no great, antiderivative for e to the negative x squared. That again, if you plug this into Wolfram alpha or whatnot, again, it's going to give you some nonsensical function out. because there is no way to express this antiderivative using any combination of previously known functions. And yet we can still use power series in order to evaluate out this integral from 0 to 1. So please pause the video, give this one a go, and when you're ready to see the results, come back and hit unpause. All right, so let's go ahead and walk through my solution here. Again, we need to use power series, so we're going to start off with the power series of e, or e to the u here, and we're going to substitute in everywhere we see our variable u, we're going to put in negative x squared. So that's just this work right here. Then we're going to go ahead and integrate. So when I integrate, and again I'm kind of looking at this right here, we can see that we have quite a few constants that are along for the ride. So these all stay the same. And then when I integrate x to the 2n, we raise our power by 1 and we divide by that new exponent there. So that's how we jump to that line. And then next up, right, the last bit is that we just need to plug in 0 and 1 everywhere we see an x. So notice that, again, back here, this is the only x that I see. So if I was to plug in 0, of course I just get 0, right? I get lots of powers of 0, and they all just go away because 0 raised to any power is 0. If I plug in 1, however, well, still it simplifies down quite a lot. Notice that I've only written just 1 right here, right? Because 1 raised to any power is 1. So we get this. This right here would be our final answer. Now, of course, if you wanted to actually see what this kind of looks like, we could write it out in the expanded form. So we see it's 1 minus a third plus a tenth minus a 42nd and plus, and it keeps on going, right? And we're adding subtractors smaller and smaller values, or that answers around 0.7468, and it keeps on going on and on and on, sort of deal. So, but yes, this right here would be my final answer. So, okay, with power series, we can evaluate out integrals that otherwise, right, again, using just our chapter 7 stuff, there's no way to evaluate this out. We could spend a long time spinning our wheels and never make it, right? Again, U substitution, integration by parts, any of this stuff can't be used in order to evaluate this out. Again, you can go on Wolfram and you can see, you'll learn about this function ERF. But anyway, so yes, power series is the way that you have to do these sorts of problems. So this is, again, something that Maclaurin series, Taylor series, that's what they're bringing to the table. That's why they're useful. All right, thank you so much for watching, guys. Again, if you have any questions about any of the stuff that we brought up in this video, please post on Piazza or visit my office hours, but please reach out for help. And yeah, I'll see you guys next time.